Okay, so for the next module, we'll be talking about the rate expression concept. So the rate expression is a way of expressing a reaction and the rate at which it occurs using letters and symbols. So one might say that rate is proportional to this symbol. This symbol signifies the rate is proportional to the concentration of A. And if you add, or you could write it in this way, that K times the concentration of A, with K being a constant. The rate expression is an experimentally determined equation that relates the rate of reaction to the concentrations of the substances in the reaction mixture. So another way this could be expanded, if there are more than one substance involved, could be A, B, and if there's an exponential relation, could be A, B squared. So the K value is known as the rate constant, and this is a constant of proportionality relating the concentration in the experimentally determined rate expression to the rate in the chemical reaction. And then the exponent here is known as the order of the reaction, and with respect to a particular reactant, the power of the reactant concentration is in the experimentally determined rate equation. So in this particular rate expression, the order of reaction is 2 plus the exponent for the concentration of A, which is 1. So the order of reaction is 3. So to experimentally determine the order of reaction, we can look at a worked example here. So we see that the concentration of A and the concentration of B and the various rates. So we can see here that for the first experiment, when the concentration of A is 0.1 and the concentration of B is 0.1, the rate expression is approximately 0.5. However, when we triple the rate of A, but we keep the concentration of B the same, the rate would increase by 9. Whereas the concentration of A increases by a factor of 3. When we see this, there's an exponential relationship between 3 and 9, signifying that the rate order of reaction of the concentration A is 2. So to determine the order of reaction for the concentration of the substance B, we would have to do the same thing, except we would have to make sure that the concentration of A would be the same, so we can compare the rate. So that would take place in experiment 2 and 3, and with concentration of A staying the same at 0.3 in both experiments. With the concentration increasing from 0.1 to 0.2, or multiplying by 2, but the rate staying the same, there's no relevance to the rate, as in there's no proportionality increase, signifying that the order of reaction for concentration B is 0. So to write the rate expression, we could do rate equals K times A to B 0. And of course, anything to the power of 0 is equivalent to 1, so this can be cancelled. So, for example, to actually determine this value of K, we can substitute in known concentrations from our experiment table over here to determine this value. So we know here that the rate, looking at experiment number 1, we see here that the rate is 0.5 K, and then the concentration of A is 0.1. So 0.1 squared is equivalent to 0.01 when we divide both sides by 0.01. And we would get a constant value of 50. So this is how you would determine the rate expression. So then, there are different ways of graphically expressing um, the different orders of reaction. So the difference between a zero order graphically is that there's simply no reaction, no relevance, and a graph of a zero order reaction would simply look like this, with concentration on the y-axis and time on the x-axis. So this is relevant to the first order. So the rate is directly proportional to the concentration. So we would see a gradient of 1, and it would look something like this. And finally, for second order, we would see an exponential type relationship where the order would be concentration and time, and the gradient to be increasing in an exponential rate, looking something like this.